Hello everyone. Today we are going to be going through how to do some integration using substitution. So a lot of times there's no direct rule that applies when we look at some more complex integrals. So over here, integration by substitution is really all about recognizing some patterns and transforming some complicated, messy looking integrals into much simpler ones. So let's walk through this with an example. Let's evaluate the integral of 2x times cos of x squared. Now, looking at this directly, and if we try to integrate this directly, there's no straightforward rule that applies. But we do notice something very interesting over here. We know that the derivative of x squared is 2x, and we also have 2x sitting out the front of this equation over here. So integration by substitution is really all about recognizing patterns in regards to defining a function and noticing whether or not we have its derivative within this equation as well. So in this case, we will be defining u as x squared, and we know that its derivative would be du dx, which is 2x. So really, we could rewrite this integral as the integral of du dx times cos of u dx. Now note over here that the dx's cancel out, and this leaves us with the integral of cos of u du, and we can integrate in terms of u because we have this du at the end over here. So we are integrating with respect to u. So if we begin to integrate this normally, this is a much simpler equation for us to work with. Integrating this normally, this would equal sine of u plus c. And if we substitute our u back in, so we define u as being x squared, we can now substitute it back in to our equation over here to give us the answer sine x squared plus c. And there's our answer. So really, the trickiest part about integration by substitution is recognizing and defining an equation and recognizing its derivative within our integral as well. Let's have a look at another equation. Let's try to integrate sine of x times cos square of x dx. What we notice with this equation is that our derivative of cos x is actually negative sine x, and we can work with this over here. If we define u as cos of x, we know that du dx will equal negative sine of x. Although this is not the same thing over here, we can manipulate our integral to make this work. Let me demonstrate. If we rewrite this integral, this would give us cos squared of x, which can now be written as cos of x all squared. And because we defined cos of x as u, this can be written as u squared. So the cos squared of x can now be written as u squared. This leaves us with our sine of x. Now we already defined du dx to be negative sine of x. So what we can do is we can write this part of the equation as negative sine of x. Now we can substitute this du dx into this part of the equation, giving us the integral of u squared times negative du dx. This negative can be put out the front of the integral, and again these dx's will cancel out, leaving us with negative integral of u squared du. Integrating this equation should give us negative u to the power of 3 over 3 plus c. Once again, we can make the substitution back. So before we define u as being cos of x, so this can now be substituted back to give us negative cos of x cubed over 3 plus c. Let's have a go with another equation. Let's integrate 5x squared times x to the power of 3 minus 1 to the power of a half. Have a go at finding our u and its derivative for this part of the equation. Now, once again, this one is not as obvious. If we define our u to be x to the power of 3 minus 1, we know that du dx will be 3x squared. Although we do not have a 3x squared out the front, we do have an x squared that we can still work with. Like we did with the negative sign, we can manipulate our integral to make this work. So if we rewrite this integral, this would give us the integral of u to the power of a half, so that's this part of the equation, leaving us with 5x squared. Now, once again, we defined du dx as being 3x squared. So we can rewrite this 5x squared as being 3x squared times 5 over 3. So 5 over 3 times 3x squared should give us 5x squared, which is what we had here in the first place. So if we rewrite our integral using this manipulation, this would become the integral of u to the power of a half times 5 over 3 times 3x squared dx. As we defined before, our du dx equals 3x squared. So we can make the substitution for this 3x squared now. So we can rewrite this integral as u to the power of a half times 5 over 3 times du dx dx. Once again, these two dx's can cancel out, and this 5 over 3 can come out the front of the integral, leaving us with u to the power of a half du. Integrating this, we should get 5 over 3 times u to the power of 3 over 2 over 3 over 2. And if we go to simplify this, 3 over 2, this should simplify to u to the power of 3 over 2 times 2 over 3. Not to forget our plus c at the end. Simplifying this equation further should give us 10 over 9 times u to the power of 3 over 2 plus c. Remembering that we defined u as being equal to x to the power of 3 minus 1, we can make this substitution back into the equation. So this should equal 10 over 9 times x to the power of 3 minus 1, all to the power of 3 over 2 plus c. Let's now have a go at integrating 3x e to the power of x squared dx. Looking over here, we can define x squared as being u, so u equals x squared, and we can see if we take the derivative of x squared, this should give us du dx equals 2x. Once again, I know that we have a 3x out the front of this equation, but just as we manipulated our integral before, we can do it again to rewrite our equation with a du dx in there. So if we were to rewrite this equation, we can write it as the integral of not 3x, but that 3x can be rewritten as 2x times 3 over 2. So if we rewrite the 3x as 3 over 2 times 2x, we can make this substitution for 2x into the equation. So this should become the integral of 3 over 2 times du dx times e to the power of x squared, which we defined as being u, so making that substitution over there as well. Not to forget our dx at the end. Once again, these dx's can cancel out, and this 3 over 2 can come out the front of the integral, leaving us with 3 over 2 and taking the integral of e to the power of u du. The integral of e to the power of u should give us 3 over 2 times simply e to the power of u plus c. Once again, let's not forget to make the substitution for u back into this equation. So we defined u as being equal to x squared before, and we can make this substitution back here now. So this should simplify to 3 over 2 times e to the power of x squared plus c. Hopefully this gave a bit of an overview on how to approach some questions involving integration by substitution. This is all about recognizing patterns and recognizing when we have an equation and its derivative within our integral. As always, let me know if you have any questions. Otherwise, I will see you next time.